let's start our move into three-dimensional quantum mechanics. Now, I think we're going to find that a lot of stuff, especially early on, is very similar to what we've done before, very similar to physics. But of course, when we're adding more dimensions, we're going to be adding more mathematical complexity. And so here we have a vector R with its x, y, and z components. And so now we have our same time-dependent Schrodinger equation. And our capital psi now is going to be, instead of being a function of just one spatial dimension, now we assume this can be a function of three spatial dimensions. And so we got a few things we're going to go through and just sort of adjust in our time-dependent Schrodinger equation. So first of all, the probability of finding a particle in the 3D region of some differential element dx, dy, dz is just what we would expect. The absolute square of the wave function times that volume element. And our normalization condition is going to be the same thing over all space. That's going to be equal to 1. So again, when it comes time to do this sort of thing, it's the same ideas we've been using, just a little bit more, I think, mathematical complexity. And furthermore, we've dealt with the operator that represents momentum, and we've been dealing with these. And so now we can separate three of these, one for each spatial dimension. And so we've been using py or px, but we can also write out py as so, and pz. This gets a little bit cumbersome, so we like to combine these into one piece. And so we're going to say that the total vector momentum operator that represents momentum is I h bar times the del operator, which you've probably seen this before, but it doesn't hurt to go through and discuss this a little bit more in depth. And so this is the operator here of these three partial derivatives in their vector directions. So again, this is a vector in the x direction, a vector in the y direction, and a vector in the z direction. And so over here we can write our Hamiltonian in three dimensions, same sort of way. So it's p squared over 2m plus our potential, although now our potential or our momentum is this vector here. And so if I write this out, we'll get 1 over 2m. And if we square this up, we get the momentum in the x direction squared plus momentum in the y direction squared plus momentum in the z direction squared plus z. And if we work through this, we get 1 over 2m. And when we square these guys, we get negative h bar squared d dx squared, negative h bar d dy squared, negative h bar d dz squared, plus our potential. And so, writing this all out, we get negative h bar squared over 2m del squared plus z. And so this del squared is the Laplacian, and this just works out to be these three partial derivatives added up like such. And so that's how we can write our time-dependent Schrodinger equation in three dimensions. So, the time-dependent Schrodinger equation, and just like last time, all right, we can say that if our potential is independent of time, the TDSE, this is the time-dependent Schrodinger equation, is separable, just like in Chapter 2. And so we can find solutions to capital psi in terms of our lowercase psi as a function of r, and then actually the same time-dependent piece we had before. So again, this is the new piece that's dependent on 3 spatial dimensions, and we left with our same time-independent Schrodinger equation. So this will boil down, again, very similar case to last time, just now that we have this mathematical complexity of 3 dimensions. And so the time-independent Schrodinger equation is going to be key for us. So here it is. And we're going to find, just like before, that we're going to be able to write any solution as a sum, a linear combination with Cn coefficients of these separable solutions. Now, we're going to find that many of the applications we make in 3D are going to be with what we call central potentials. And a central potential is a potential, so our potential is assumed to be a function of r, but ends up being only a function of the absolute value of r. Like so. And so potentials that only depend on the distance from the origin. And for example, we're going to look at the hydrogen atom, and so we have a really heavy proton that we'll just assume is at the origin, and then we'll use our vector r coming from the origin. And so if we imagine that our potential here is our electron, and so that potential, the Coulomb potential between them, only depends on that distance from the origin. And so that's going to make spherical coordinates super convenient. So the next step for us is to go through and remember a little bit, refresh our memory a little bit about spherical coordinates. So just a refresher on spherical coordinates. So if we have our vector r here, then we have 3 coordinates, r, theta, and phi. R, of course, is the length of that vector. Theta is the angle coming down from the z-axis. And if you were to look at this vector in the xy plane, sort of like this here, then the phi would be the angle here coming from the x-axis. Now we're going to do a lot of going back and forth between the Cartesian coordinates and the spherical coordinates, and here would be our definition, or at least one way to write these out, like so. So you've probably seen these before, but if not, again, this is really handy when we're looking in central potentials. And so just as a refresher here, here's a clicker question. So in Cartesian coordinates, the volume element is dx, dy, dz. In spherical coordinates, the volume element is what? Right. Hopefully you got that the correct answer here is E. And so it's not as simple as just dx, dy, dz. The reason for that is if we go back and look at spherical coordinates, we find that the actual directions r hat, theta hat, and phi hat are constantly changing. And so let's imagine that we have this r vector, and it's in the zy plane. And so this would be my theta, and if we were drawing our projection, it would look like this here. And so this would be our phi equal to pi over 2. Then if we were to write out our coordinate system, r hat would be pointing that way. The theta hat would be pointing that way, and into the page here would be our phi hat. And of course, so these directions are always orthogonal to each other, but depending on where you are, they're at different places, and that's where these extra pieces come from. So one way to kind of just look at this to check yourself is let's try to calculate the volume of a sphere radius r using these pieces of a triple integral. So my volume element would look like this here. And you're integrating from 0 to r for the dr, 0 to capital R rather, 0 to pi for the theta, and 0 to 2 pi for the phi. So the phi is, excuse me, this should be a phi. There is no phi dependence, and so we just get out phi evaluated from 0 to 2 pi. And the rest of our pieces here. And so this will just give us a factor of 2 pi from that first integral. And so next, I'll go ahead and do the theta integral. And so that's just a sine theta. And so that's going to give me negative cosine theta evaluated from 0 to pi. And this is times our 2 pi and our r squared, which we haven't done yet. And so this here, when you plug in the theta in the 0, this is going to give us a factor of 2, right? So this will be negative cosine theta plus cosine of 0, which is going to equal 2. And so that'll leave us with 4 pi times the last bit of the integral here. And of course, in this case here, it'd be 4 pi, and this would be r3 divided by 3 from 0 to r, which when we're all said and done, gives us our equation of the volume of a sphere. So now we turn to what we spent chapter 2 doing, which is to solve the time-independent Schrodinger equation. Now here we're in three-dimensional spherical coordinates, so it's going to be a little bit trickier. The first thing I'm going to do is just rearrange this equation a little bit, isolating the Laplacian times the wave function. Now, if we write this out in spherical coordinates, we get this expression here. You may have seen this before. This is essentially just a coordinate transform into the spherical coordinates. It is not very easy to derive, but this is what we get. And so what we're going to do is what we do with partial equations in physics. One of our first things we try is to put in a separable solution. So one function we'll call capital R, that's a function of R, and one function I'm going to call capital Y, which is a function of theta and phi. And we're going to plug that in and go through and see how it separates, just like we've done before. And so again, remember that what we're taking here is we're saying, all right, so our function, and just for a shorthand, I'll write it as R and Y, where R only depends on R, and Y depends on the two angles. And so I'm going to plug this into here, and so when I do that, one of the functions in each of these partial derivatives, right, one of them will essentially be constant and can come right out into the front. And so we're dealing with the R. The y is going to be the one that's going to be essentially constant. So I can pull that out, so I get y over r squared, this term here. These partial derivatives turn into pure derivatives. So r squared dr over d little r. And I'll write a box out here as we'll see. And then for the two angular partial derivatives, the opposite will happen. The r will slide on through as a constant, and the y will be what we'll be taking the derivative of. So we get capital R over little r squared sine theta, our partials of theta. These remain partials because this function has still two independent variables. So we write it like this. And then over here, little r squared sine squared of theta, partial of that y over phi squared. And then on this side, we're going to get the 2m over h bar squared e minus v, and then here I'll just write this out as r y. Now, what we often do here is we're going to divide by the wave function written out as y over r. We're also, just to clean things up, going to write r squared on top. So we're going to multiply both sides of the equation by little r squared over the wave function y times r. And so the r squared is going to serve to cancel out these pieces here, just to clean this up a little bit, and it'll add an r squared over here. And so now when I divide through by y over r, we'll see, like in this term here, I'll be left with 1 over r d dr r squared, like so. Now I'm going to bring this piece over. And so since on the other side of the equation, I'll do that by just incurring a positive sign. So 2m r squared over h bar squared e minus v. And when I divide through by y over r, these two cancel. And so I get nothing over there. And over here, of course, the y cancel, and I get the r left on the bottom. And with the two angular pieces, of course, the opposite will happen. These r's will cancel, and I'll be left with 1 over y out front of those. And so when I go through and write this out, it'll look something like this. This is definitely the kind of thing that I advise you to go through at least once in your life, just to make sure everything makes sense. All right, and so when I'm all done here, this equals 0. And so we have the situation that comes up that we like, which is this side of the equation is only a function of r, and this side of the equation is only a function of the angular pieces. And so when that happens, what we can do then is equate both of these equations to a constant. Now, what happens a lot of the times is we'll write this constant in a special way because we know we've done this before, essentially. We know where it's going. And so the funny constant will be a little l times l plus 1. And over here we'll call this negative l times l plus 1. And so these two equations then will work out to be like this. And so this is our radial equation. This is our angular equation. And again, here's our special constant that we're dealing with here. We just multiplied by sine squared theta just to kind of clean that up a little bit. And so we'll spend the rest of this section next time going through and figuring out how to solve for both of these equations.